Yeah, no, I want to show that not only they're equal, but they're equal to the average of the.
30 or even 50 like that, it can be 5.
Yeah, if we rescale to be kind of with a normalization 150, they're going to be equal to the average of what we started from. So that's my hint for part C. Actually, in part C, you don't really need to do much. Kind of the idea is to initialize the initial distribution with the ages of the people and then have them communicate with each other according to the transition kernel. And so you can think of each state in the Markov chain as one of the people, and they talk with their neighbors according to the transition kernel. And what do they exchange? They can exchange their ages according to the transition matrix here. So that's my hint. Maybe I said too much, but think about that. That's the suggestion for part C. So think of the people as nodes, and think of their communication with one another. So you can only talk to your neighbor. Think of talking with your neighbor as like applying a transition matrix, which is this one. And then think about what will happen if you initialize your initial vector to be the ages, or some normalized version of this. What happens if, as time goes to infinity? So I would say the answer is already there in B. You just have to interpret things.
Okay, I'll give that some thought. Thank you.
Yeah. Yes?
So would a better formulation of the problem be then, like, how can an individual person at the table figure out the average age of the group?
Correct, yeah.
Okay.
The individual person at the table is only allowed to talk with neighbors.
Mhm.
So let's say our table is kind of the three of you, the two of you, and me. So we have 6 people on the table, but my neighbors are here. So I can only talk with you or you. So I have no way of asking, for example, over there, Jason, what's your age, right? I cannot do that. But I can ask both of them, what are you maintaining as your, so you're allowed to store kind of an estimate of ages of everyone. So I can ask, what's your estimate of Jason's age? And you can tell me, and I can update my estimate of Jason's age. But you can then ask Aram, hey, what's your estimate of Jason's age? So we're allowed to talk with each other, but only neighbors. Does that make sense? Yeah, so think of the P vector as estimates of the ages, and think of the capital P matrix as this communication process. So whenever we exchange information in one step, it's like taking a transition in this Markov chain. Yes?
I don't know if it's like giving away too much, but like the final answer that one person should get should be the average of all those numbers right there, right?
Correct.
Okay.
Yeah, exactly, exactly.
So like whatever our algorithm that we come up with, it should result in that.
Yes, that's right, yes.
Okay.
Right, your algorithm in the end should lead to, yeah, in the end I should know, yeah, true. Actually, yeah, what I said was maybe misleading. I'm not interested in Jason's age, but I'm interested in the average age. Yeah, correct.
Okay, gotcha.
Yeah, so I would say there's not much more than part B. Kind of all the computation is already done in part B. It's more about reinterpreting it in this context in part C. There's no, you don't have to design a new algorithm. You just need to say, the algorithm in part B already works for C if I think of this way and think of this way. Yeah, maybe that's the trickiest problem, or the one that's most abstract.
I think
Yeah.
I still have trouble thinking of it in the Markov chain context because I want to say like why can't if Kevin's my neighbor, Jason's his neighbor, why can't I just ask Kevin what his age is? And that's like why would Kevin be giving me an estimate of Jason's age if he knows Jason's age?
Yeah, I guess you could do something like this, where yeah, I guess the motivation for this, or the thing we're trying to avoid, is that there might be a person that's more than 2 hops away from you. So then we need to do multi-hop communication, meaning you need to ask your neighbor of the age, not of his neighbor, but of 3 neighbors away. So for him to give you this information, he also needs to propagate. So the communication gets more complicated, right? Your message now requires not just talking with one person away, but maybe some multi-hop. To get your question all the way here, you need to pass through multiple hops. And the benefit of this algorithm you'll come up with is that communication only happens with your neighbors. You never have these queries that have to traverse through the communication graph. That's the motivation for it, yeah. But the solution is pretty much what we do in part B already.
I'll give that some thought, thank you.
Yeah, think about it a bit. So again, for part C, you don't need to come up with a new algorithm. You need to interpret what's going on in part B in the context of 5 people sitting at the table and talking to each other, where the people are the nodes, and the transition matrix is the communication. So if you can kind of interpret what's going on, I think that's the answer, yeah. Okay, more questions? More homework questions, or we can discuss the project briefly if there are no more questions on the homework.
Tiny question about,
Maybe like that one there.
I'm about like, how do you calculate the
Okay, how do you calculate P infinity? My suggestion is to look at the slides. We have a theorem which says that. Which theorem is that? Yes, Perron-Frobenius theorem tells us how to compute P infinity. Good. That's our question.
actually, never mind, I think it's okay.
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 All right, then let's talk about the project. Did people start looking at the project? Who has downloaded it and looked at the data? Okay, not many people. Okay, some people, yeah. Let's see. Let's look at this. Okay, so just some suggestions. Yeah, so in our project we have environments like this. We have an agent here that can move left, right, up and down. And there's a goal state denoted in green here. And there's a door on the way which can be opened or closed. So if the door is open, you can just go directly to the goal. But if the door is locked, you first need to go get the key, get to the goal, unlock it, and then get to the goal. Question or comment?
Does that like sort of imply that there's like a dual cost for the door, like so that if the door is well, oh, you just can't trip, it's an obstacle?
Yeah,
or
it's
is
a,
it-
exactly, yeah, yeah. If it's closed, you cannot pass. If it's closed, the only thing you can do is get the key and open it. Once it's open, it's like there's no obstacle, correct? Yeah, it's, yeah. Right, okay, so in terms of hints, really, yes, today we discussed some more algorithms, but really the only algorithm we know is dynamic programming, so you should try to do the project using dynamic programming. I know maybe in other classes you've done Dijkstra or A-star and blah, blah, you can think if I can use that. No, the idea of the project is to use dynamic programming, okay? So that's a hint, or strong one,
So
yes.
just to clarify, even in the deterministic cases for this project, use dynamic programming?
Yes,
Okay.
use dynamic programming for everything, yeah. Okay, that's the suggestion. Then the part that might be unclear is how, right, or how, so think about dynamic programming. As an algorithm, there's nothing to change or to think. It's there on slide whatever on lecture 4. So the algorithm is well defined. The only part that you have to think about is what is the MDP, meaning what are the states, what are the controls, what are the stage costs, what is the planning horizon, what is the terminal cost. So the part where you spend time thinking is this, right? How do I define the state? How do I define the control? How do I define the costs? How do I define the planning horizon, and so on? So those are the things you can change. Once you define those, you just you implement the dynamic programming algorithm, but there's nothing to think after that, right? So the main part of thinking should be definitions of states and costs and controls rather than algorithm. The algorithm is there already. All right, then let's see, other suggestions. So even some of these are easy, right? For example, what are the controls? Well, those are already given, I guess, somewhere here. So the agent has 3 regular actions and 2 special actions. So what are the controls? How many controls are there? 5. What's the control space? Is those 5 possibilities. Okay, the controls are easy, but the state space is the one that needs a little bit of thinking. So let's think about part A first. Yeah, I also suggest doing part A first and then part B. Okay, don't do part B first and then A. Okay, starting with part A. Any ideas of what the state should be? Yeah.
I would just assume based off of like looking at those figures, just like each cell is like a coordinate, and that coordinate can be treated as a state.
Yes, so that would be something like position of the agent, right?
Yeah.
Do we need anything else?
Can we include whether the state has the key or if there is a door in the state?
Right, so we might need to keep track of, do we have the key or not, and is the door open or not? Yeah, question?
Yeah, no, I want to add something, so we probably need to keep track of the heading.
Yes, correct. So we will need position and orientation because of the way our actions are defined. We can turn, but we cannot move absolutely. Yes, so we need heading, we need position, and potentially we need to know if the door is open or closed and whether the door is open and closed. So yeah, one more point, I don't know if it's obvious in the code we gave. For part A, you can look those up. So whatever your map is. So in part A, you don't necessarily need to have that as part of the state, meaning whether the door is open or whether you have the key, because you can always check in the environment. But in part B, you will need that for sure, and more. In part B, there is variation on where the key can be, where the goal can be, and where the doors can be. So the hint or suggestion is to make that part of your state. So in some sense, your state in part B is larger than your state in part A. One more difference between the two. In part A, there's 7 environments. So you're allowed to run dynamic programming 7 times, 1 for each environment. That will give you the policy, you execute it. In part B, there are 36, or I forgot how many. There's a bunch of environments. You're allowed to run dynamic programming only once. Okay, that's the difference between A and B. In B, you need to run dynamic programming once, and that should give you a policy that works across all 36 environments. In part A, you are allowed to run it for every environment again. Yes?
So in part B, if I understand correctly, there's like 36 scenarios, and I've looked at like a few of them, but basically, like when you have your optimal control policy, what should happen at least is that like the simulation like chooses one of those scenarios at random, and then your control policy is random.
Exactly, right. Yeah, you're not allowed to look at the map and recompute your policy. It's the opposite. You compute your policy once, then let's say your opponent, me, I pick a random environment and I run your policy on it, and it should work, whichever one I pick. Yeah.
So randomness means all the 4 things we are changing: key, door, start, and goal.
Yes, I think that's pretty much it. I think there's either code, I think there's code of how the random environments are generated. So take a look at that and see what can vary. I think that the things can vary is the key location, the goal location, and whether doors are open or closed. Yeah, I think that's about the only
Oh, it's
variation.
not sure like the door will always be closed. It might be open, it might be closed.
It might be open, yeah. If it's open, you don't need the key, right? You go directly. But if it's closed, then you do need the key. Yeah. And if there are 2 doors and one is open, but the one that's closed is maybe closer to you and you can grab the key, maybe that's better, right? So dynamic programming has to figure this out. Is it better to grab the key and unlock, or should I go the longer way where it's open?
So there are more than one door.
Yes, in the random environments, I think there are more than one door. Yeah. Yeah. Okay, more questions? Yeah, well, one more point for me, how to define the costs. So the costs are not defined in any way, so you're allowed to define them in any way you like. I would say you don't have to overthink it. I mean, you can really define them any way you like, but define them in a way that makes sense, meaning we are trying to get to the goal quickly. We don't want to be doing circles around. So one very simple way of defining, again, the cost can be really simple. Any action costs 1, except if it's getting you into an obstacle, then it costs infinity. So I would define it something like that.
Can we take like utility on this one?
You can make it fancier if you want, but I'm saying the simple definition is enough. Everything costs 1, except if you're hitting an obstacle, then it's infinity. That's the simplest possible, and I think that's fine.
Just a quick question about 2 doors. So,
Yeah.
when we are dealing with 2 doors, do we consider 4 different states or just 1? one of them is open.
You should consider two states which can have values true or false, for example. So you have one state of door 1, could be true or false, and you have another state of door 2, which could be true or
I
false.
was thinking like 000101.
Yeah, you can think of it that way. Yes, exactly. That's good. Yeah. Comments, questions? Yes.
I still need to look at the code for the random section first, but in general, we'd only be able to know if the door is open or closed. Or the state, we'd only need to be able to know the state of the door if our agent is right next to the door.
I think you can look up the door state at any time. So in the beginning of time, at time 0, you can look up the door states.
Oh,
think so,
okay,
yeah.
regardless of where the agent is.
Yes,
like-
yes. There is a version of this problem where there's some limited visibility and you don't see the door, but we removed that here. So you can look up the door state at any time, or right away. Yeah, you can know the door state immediately.
Oh, okay.
So you don't need to get to the door first to check. Yeah.
Got you, but
I
the
think-
key,
yeah.
the key position is random as far as we know.
And you can also look it up at time 0. But again, in part B, you're not allowed to change your policy.
Right, okay.
Yes, but you can look up the key position, the goal position, and door position right away. There should be a function which tells you that directly. Yeah.
Okay.
Yeah, so you're allowed to use that function and look up the key, the door position, state, and the goal. Yeah.
Gotcha.
You're allowed to look them up directly. You don't need to get to there. Yeah, there's no stage where we're searching for the key or something like that.
Okay.
You know where the key is. Yeah.
Gotcha.
Okay, more questions? Yes.
So couldn't we just use the solution for B and A?
Right, yeah, that's a common question, and the answer is yes, technically, but the maps in A are not generated from the same random distribution, so you will have to enlarge the randomness in B in order to be able to solve A as well. And on purpose in B, we chose like a small set of things that can change so that the number of states is not. So the number of states will still become quite large here, you'll see. You're going to be dealing with thousands of states, but it's still manageable. Yeah. So I would keep them separate. Do A first and then B. Yeah. Other comments or questions? Yeah.
I had a question regarding like the planning horizon.
Yeah.
So, I know this isn't part of the dynamic programming algorithm that we discussed, but my thinking is that like we can set the planning horizon to be something that's countably infinite, or like it's like.
So in all of what we discussed so far, the planning horizon has been finite, and we start backwards in time. So if you set it to be countably infinite, you will never terminate.
Yeah, it never terminates.
So, but today, when we did the equivalence between shortest path and optimal control, we said that the planning horizon should be, what did you say today?
Oh, it was states minus.
Number of states minus 1. So that's roughly. So I would say anything larger than this is fine. So you can approximate.
Right, okay.
So if you know roughly how many states there are, just multiply with 2 and that's your planning horizon. We also discussed how to terminate the algorithm early.
It won't
So
change then.
so you can stop early, even if you pick the planning horizon to be really large and you don't need that many steps. If you do the early termination thing, that should be fine.
Makes sense.
Yeah, our problem is stochastic or deterministic?
Well, the no map is deterministic.
Yeah.
But the random map is stochastic.
The transitions are still deterministic, so our problems are deterministic.
Oh,
Yeah.
okay.
Yes. Just in the random map, the initial state is random maybe, but you get to see what it is. So yeah, we can treat them as deterministic. So yes, I would say you're allowed to use the dynamic programming from the previous lecture or forward or backward dynamic programming from this lecture. Those are good. But don't get into the extra and because the next lecture we're going to discuss A star. It's not meant to be done for this project. Even though you can start doing if-else sort of statements and using if the door is open, plan an A star path to the goal. If the door is closed, plan an A star path to the key, and then plan an A star path from the key to the goal, and so on. That's not the point. The point is to figure out how to define states and use dynamic programming. We have another project where we're going to use A star. Yeah. Or planning. Yeah. Yes.
This method that you just said about planning using star, this and using dynamic programming, will there be any difference in optimality?
Dynamic programming will give you an optimal solution. This A star method, I don't know. You're starting to do something questionable with the if and the else, so depending on how you define those, you might still get an optimal solution or not. Yeah, but dynamic programming guarantees optimality, yes.
But A-star also promises optimal solution.
From point A to point B, right? But if you start, yes, okay, so can we reformulate this problem in a problem that is solvable by A star? I would say yes, because it's if we can formulate it as a deterministic optimal control problem, today we discussed there's a way to convert it into a shortest path problem, and A star can solve shortest path problems optimally. So yes, there is a way to use A star to get the optimal solution, but that is trickier. It's not having if-else statements with the door being open or closed. It's more like formulating it as an A star, as a single A star applying problem. So yes, it can be done. Yeah.
Then would it be D-star?
No cost of changing. Yeah, no need for D star. So D star would be if you start moving, you get the environment, your agent starts moving, but the door closes in the mid. As you're moving around, if the door changes, then you would need something like D star.
If I remember correctly, earlier we were discussing like D-star handles like if some obstacle comes into the picture.
Right, yeah. If during execution things change, yeah.
Right.
So if the door closes as you're moving, then you could do D star.
Oh,
But our environment doesn't change during runtime. Yeah, it's fixed. Yeah, the doors don't open or close randomly. Yeah.
Just a quick question. As you mentioned, when the map changes, we use D-star to the optimal path. But can dynamic programming? So the only difference that I saw between dynamic programming and D-star was the way open loop was open set was used, I guess. So will dynamic programming adapt to it or?
Okay, we haven't discussed yet D star or changing environment. So wait with this question until we get there. Yeah. Right. So we haven't even said what the D star algorithm is yet. So George, yeah. Yes, all questions sounds good.
When I was doing questions before, so I encountered doing dynamic programming for process-based randomness.
Yes, correct.
So, for example, I'm doing the backward. I know like the v for t equals 3, and I have v equals 2 being a piecewise function.
Okay.
Because it's making decisions, right? Because for some x, we're going to make that yield to minimize function. That's how closed loop function works. So with such a piecewise function, when I go back to times that equals 1, it becomes, addition, the computation of the expectation requires addition of these different functions at different boundaries.
I see.
It's very complex. There are some boundaries are overlapping on the model.
I see. But we had I think in our problem there's really a finite number of states you can go to. So maybe you don't need to think of the function as a continuous thing, but just look at the states. Let me check. So you can just think of the. Let me check to make sure I'm answering the right question.
Professor, is your mic on?
No, I stopped.
Is it? Oh, okay.
We're not even recording anymore.
Okay.
Yeah. Good question. During the lecture, now I'm not.
I learned an A.
Let's see. Yes. So let's see. So let's look at this. Yeah. So you're starting in state 2.
Yes.
And you can then think of what are all the possible states. So your controls are either -1 and 1, and your noise, for example, let's look at, and your noise can be -1 or 1. So really you can, and your planning horizon is 3 steps. So you can only go on the integers, right? You can go from 2, 1, 3, 4, 5. So, and then in 3 steps you cannot go further than something like 2 plus minus 3, so you can go from -1 to 5. Those are, so you only have 6 states, so you don't have to consider anything else. You just need to compute the value of a function in those 6 states.
So as in continuous case, we have to have these functions.
Correct, yeah. If you look in continuous case, it's much trickier, but here you can simplify it. Yeah.
Okay. So you mean just don't use algebra, just use a real number.
Correct, yeah,
Yeah.
your states are only 5 or 6,
I
yeah.
see.
So just compute the value at those 5 or 6
Right.
states, and that's it, there's no other possible states, yeah. Because you're computing the value at some intermediate continuous values, but you can never get there. Yeah, true, if you initialize at pi or at e at some weird number, you will be able to get to intermediate states, but the initial state is 2, so let's focus on that, yeah. Yeah, yeah. Okay, I can take last question and I need to go. So who wants the last question? Go for it.
I have a question for B. So the noise can be answered from -1 to 1. So can you just like calculate the cost the same way as in 4A, or does the
Yeah, I think
probability-
in B there's this hint, but to be honest, I don't remember what I meant with it. So I think you can ignore the hint and just enumerate the.
Okay,
So in B is more like practicing the definition of the value function.
Okay, so I can just like find out the state it can be and like just disregard the probability of using the state.
Exactly, yeah. Weight the costs with the probabilities and check which sequence of controls is the optimal one. Yeah. Maybe B is a little bit annoying because there's like 8 or 16 possible paths. So you have to enumerate all of them.
If the probability is like half, I can just like disregard the probability.
What do you mean by disregard the probability? There will be different likelihoods of following the different paths. So you need to keep track of what's the probability of following this path and what's the associated cost. Because when you're computing the value function, it's the expectation, right? So you need to average the cost along the paths times the probabilities of following the
Yeah,
different
but
paths.
at the end, like reaching some certain state would, the probability of all these states at the end should be the same because the probability is half and half.
Oh, I see. Yeah, right. Right, because the probabilities are always 1/2, 1/2.
Yeah.
Yes, that's true. Yes, the probabilities will be equal. Yes. True, yes, so let's simplify this. Yes. Okay. All right, let's go for now. You can ask more questions on Piazza. There's office hours on Friday. I don't know if I emphasized that, but yes, there are office hours on Friday on Zoom. Yeah.
Cool.